So from the rocket's point of view, this distance right here, this is the wave crest. This would be the wavelength from the rocket's point of view. This is what they're claiming the Earth is going to get, because they don't know anything about relativity for some bizarre reason. So this is just CTR minus VTR. Or C minus V TR. Which is just C minus V over the frequency from the rocket's point of view. They're sending out a signal x times a second, a certain number of hertz. Now, if we were talking about Galilean relativity, we're pretty much done here. That this would be the wavelength that the Earth would receive, and from that we would have we would know what the frequency is that the Earth receives, and we have a relationship between f of r and f sub e. However, it doesn't work that way. The question is, what does the Earth think the distance is? I know that the proper length is equal to gamma times the length. From the Earth point of view, they're looking at this and they're seeing the signal come towards them. They now have this distance right here. So the wavelength that the Earth thinks is there is gamma times the wavelength that the rocket thinks is there. So this is the speed of light divided by the frequency that Earth sees, is equal to C minus V over the frequency the rocket thinks it's sending out times gamma 1 over the square root of 1 minus beta squared. Flipping around for some reason, that's the gamma and this is lambdas of r. So we have C over, so we have C on this side, and we have C minus V on this side. So I'm going to just divide both sides by 1 over C, or multiply times 1 over C. And so I get 1 over Fe is equal to 1 over Fr times 1 minus beta over the square root of 1 minus beta squared. We have C over C, which is 1, V over C, which is beta. That's the 1 over 1 minus beta comes from. This is 1 over F sub r, square root of 1 minus beta squared, over the square root of 1 minus beta, 1 plus beta. So different perfect squares. So the square root of 1 minus beta on the bottom cancels out with one of the ones on top. So I'm left with multiply both sides by Fr over Fe. The frequency that the rocket is sending divided by the frequency the Earth receives is the square root of 1 minus beta over 1 plus beta. Or in a more traditional form, the frequency the Earth sees is equal to the frequency that the rocket gives off times the square root of 1 plus beta over 1 minus beta. The same with sound. As the object, as the rocket gets closer, the Earth's going to receive a higher frequency. Just like when the car comes towards you. It's and it drops off when it goes behind you. So when it's going away, the frequency drops. When it's coming towards, the frequency increases. That conceptually part, that is true with light also. The formula is very different. Now, usually, I did specifically the Earth and rocket. Usually they talk about receiver and sender. So the frequency that is received is equal to the frequency that is sent times the square root of 1 plus beta squared over 1 minus beta squared, or 1 plus beta over 1 minus beta. That's if it's coming towards you. If it's going away, then the signs flip. So you think through it, should the frequency be increasing? Oh, yes, okay, then it's plus over minus. Should the frequency be dropping? Oh, well, then it's minus over plus. All right, so let's say the speed of the rocket with respect to Earth is 0.9 times the speed of light. It sends out a frequency. Negative 0.9 c, as in it's coming towards the Earth. The frequency that is sent out is 550, 5 times 10 to the 14th hertz. What will the Earth receive? Well, because the rocket's coming towards Earth, I know the frequency will increase, so it's a plus over minus. And so the frequency that the Earth receives is going to be 5 times 10 to the 14th times the square root of 1 plus 0.9 over 1 minus 0.9. Another one of those issues with the negative sign, similar to a lot of things in this particular semester, is you think through the signs. The square root of 1.9 over 0.1. So at least that piece of it. Square root of 19. And so 5 root 19 times 10 to the 14th. This is a horrible way to actually present an answer, but without a calculator. And what do you get?
2.179 times 10 to the 15.
Questions here? I think at this point I've pretty much covered everything that you might see on Thursday. All right, so we got up to, well, basically driving the speed of light. And then we started in relativity, just talking about the fact that time's really not the same for everybody. And talking about the fact that distance isn't really the same for everybody. And everything that you've learned is just a little bit off. We're going to take a break. When we come back, we'll talk about why a couple other things that you have learned in physics are not quite right also. And I'm hoping we should be able to, with next week, should be able to get to the point where we talk about walking through walls.
Is that awesome?
So tell me, what do you think of the measurements?
Relativity, that's the lab that we're doing on Thursday. Oh, the multiple choice test. So could you pause the video, please? All right, for those who missed it, primarily over here is this new stuff we did. Actually, all of this is what we did. And you can still see in white over here, because the marker board is like that. you can see the box that I drew, and we're talking about particles bouncing up against the side. Refer to the video where I go through this explicitly. All right. That should be enough. Thank you. So we're now left with so ends would cancel, but we'll just write it over here. 2/3 times the number of particles in the box times the average kinetic energy is equal to the number of particles times Boltzmann's constant times the temperature. Ends cancel out, and so my average kinetic energy is just 3/2 times Boltzmann's constant times the temperature. And so this actually is the relationship between energy and temperature, where temperature is in absolute terms. So no kinetic energy, absolute, you're at absolute zero. Temperature is zero. And then let me full circle that 3 again. That was the 3 because of the 3 degrees of freedom. All right, questions up to here? All right. So if I'm not worried about potential energy, then I could just say that my average energy is just equal to 1/2 kBT times the number of degrees of freedom. Because we're about to delve into one with only 2 degrees of freedom. But I wanted to justify why in classical physics we're connecting energy with kBT. All right. We're going to put it out off to the side burner for just a moment. We will return to it. It will seem like a completely unrelated problem other than the fact that I'm going to use the word energy, but they will connect. I'm going to pose a problem here for you. I have 6 particles. Total energy is 9 units. I can have 9 units of energy, 6 particles, so I have basically 9 broken up spread out over 6 different particles. And the question is, how many different ways can I do that? So 9, 8, 7, 6, 5. I'm going to repeat these numbers just because at some point I'm going to get to the point where I'm going, wait a second, which number is this? So I'm just going to write the numbers again just for my own clarity. And then maybe here. All right. In math, this is known as the partition problem. The slight difference from the normal partition problem is that, well, let's see, the way this one's set up. Actually, never mind, strike that last bit. All right, so, one of the ways I could do it, I got 6 particles, I could have 5 particles down here. 5 particles with no energy and 1 particle with 9 units of energy. So I have 6 particles total. 6 particles total, and total energy of 9. 5 times 0, 9 times 1. That's one solution. I could have 4 with no energy, 1 with 1 energy, and 1 with 8. Again, 6 particles, my total energy is still 9. All right, guide me through it. Ultimately, I want to know how many are there.
How many different possibilities?
How many possibilities? Pardon?
Three, 0, 1, 2, 1, 7.
3, oh wait. Say it again?
3, 0,
3 zeros.
1, 2, 1, 7.
All right. I have 5 particles there, so let's make this 4 zeros.
Yes.
Getting the total, I need 6 total. Let's just continue down that road. So that's 4, 1, 1, 4, 1, 1. And then if I kept going, it would switch and be the same thing. I do want to point out that I have 5 particles here and one up here. If I switched out that particle for that particle, right now we're just going to consider that the same thing. There's no way to distinguish between the particles. If we could distinguish, just as a little side note, if we could distinguish between the particles, so having, particle 1 here and particle 2 here, and then particle 2 up here and particle 1 down here, if we considered all that, there's actually 2002 different combinations. We are not going to do that. We're going to go to the simpler one that we can do actually in a reasonable time. Have we exhausted all the ones with 4 zeros? Oh, that's when I have 10 energy. Oh, 101. So 1, 2, 3, 4. Yep, all right. So now I have 3 down here, 2 here, and so that's 2, so 1 there. All right, what next?
Could have 3 zeros and 3 threes.
3 zeros, 3 threes. Okay.
3 zeros, 2 twos, and 1 5.
Okay.
Could have 2 zeros.
Let's do all the 3 zeros first. So you're ready to go on some of the 2 0 ones.
Yeah.
All right.
So for another one of the 3 zeros, you could do 3 1s and 1 6. Okay. Never mind.
No, that's too many.
Yeah.
You do 3 zeros, 1, 2, 1, 3, 1, 4.
So 3 zeros, then
1, 1, 1. Basically.
that's 3 ones.
No, there's 1 at 2, 1 at 3, 1 at 4.
That gives us 7 energy.
No, 1 at 2, right? So 2 plus
2, 3, 4.
yeah.
Okay. expanding off this one, we can always move one of these up and then that down, so 3, 1, 1, 1. And then keep this one here and bring those closer together. Get that one there and then bring those together. That should be it. Do we have any repeats?
I don't think so.
Alright, so 2 down here. Austin, I think you had a 2 zeros.
Yeah, 2 zeros, 1 1, 2 2s, and a 4.
Okay.
And then 2 zeros, 3 1s, and 1 6.
2 zeros,
3 1s, 1 6.
and again, whenever I have 2 categories there, I can always add energy to one and lose an energy in another. So I could have 2 here and then go to 2, add 1, lose 1. So 4, 3, and 2, 1, sorry. There's 2 more.
Three 2s, so 2 zeros, 3 2s, and a 3? No. So 2 zeros,
Yeah.
3 2s, and a 3, yeah.
Should be 1 more. So from this one right here, we could add 1, lose 1, so 1, 1, 2. So 6, 7, 8, 9. Yeah, there we go. All right. So 1, 4,